All right, okay, guys, so let's start, okay? So for today's lecture, okay, so I would like to go through the quiz 6 first, okay, just start kind of review the quiz 6, okay, so there are some kind of problems, okay, with quiz 6, okay, some students kind of don't know where to start, okay, and don't know how to kind of draw the molecule, okay. And in this case I want to spend a little bit of time kind of review some kind of most difficult question in kind of quiz 6, okay. And just make sure that you guys know how to do it, okay, because some question, okay, so what's average, okay, so far average below 60, okay, I will say, okay. So but I haven't finished review, okay, so we will see what's average, okay, so below 60, okay. All right, okay, and then hope you guys can also prepare the coming kind of exam 3, okay, so exam 3 also cover chapter 20, okay. So the quiz 6 covers chapter 20, that's the most difficult chapter, okay, so if you get kind of poor grade, okay, that's fine, okay, so because that's not easy, okay. So I won't go through all the kind of questions, okay, just pick up some question, the most students make mistake one, okay. So my order may be different from you guys, okay, so just kind of let you know, okay. So the first one I want to go through kind of the question 3, okay. So mic addition, okay. So for mic addition, okay, so first you have to know what's reaction happened here, okay. So this is kind of acetic acid ester, okay. So you see kind of this is kind of alpha carbon. It's kind of most acidic, okay. So that's will do something, okay. And more important kind of secondary region, okay. Secondary region kind of you see kind of C double bond conjugate with CO double bond, okay. So whenever you see kind of C double bond conjugate with CO double bond, okay, so you be careful, okay. So that's most likely you will do some kind of 1,4 addition or 1,2 addition, whatever, okay. But here, because this the acid kind of the relative kind of weak nucleophile, okay. So we'll do 1,4 addition. Instead of 1,4 actually kind of reality like 3,4 addition, okay. So all right. So we draw the kind of the ester first, okay. No oxygen here. Right, so this is a real nucleophile. You build bond with the fourth carbon of this guy, okay. All right. Bond between these two, okay. All right, so now we maybe all right. So that's the thing, okay, keep in mind, okay. So for the micro addition, okay, so looks like kind of 3,4 addition, okay. So the alpha the inlet at kind of fourth carbon, and then the hydrogen goes here, okay. So that's don't forget kind of right, and then next one, okay, I want to go through is say question 7, okay. Right, question 7 is kind of poor, okay, poor question, okay. So but very similar, okay. So it's ozonolysis plus the intramolecular kind of adult condensation, okay. So I just use first one example, okay. All right. So ozonolysis case we learned kind of pretty early chapter, okay. So proper chapter 11 addition chapters, okay. So the last one pretty easy, okay. Whenever you see CC double bond break up, okay, so it become kind of 2 CO double bond, okay, and you kind of the di kind of aldehyde, okay, di kind of aldehyde, okay. So those two can have kind of intramolecular kind of the adult condensation, okay. All right. So now we first draw the first molecule, okay. So the first step, okay. So break up the CO kind of okay. So we first draw here, okay. Right, original this is double bond, okay. So now it's break up, okay. So become kind of 2 CO double bond, okay. So that you have to know how to do it, okay. Right. Next kind of the intramolecular kind of adult condensation. Intramolecular condensation build up either 5 membrane or 6 membrane, okay. So for here, okay, so the data material, so you can use this one as kind of a nucleophile alpha carbon, okay, attack on the carbonyl here, okay, or you can use this one attack here, okay. So overall you should get kind of 5 membrane, okay. So 1, 2, 3, 4, 5, okay. All right. So that's here the next step, okay. You need to draw, okay. 5 membrane case, so depends on which you use as nucleophile. For example, I use this top one as a nucleophile, okay. So that's here the this one still has kind of here the already have attached, okay. Right. Oxygen, okay. And then that's here this bond kind of new bond position, okay. And then you open the CO bond here, okay. So that's your general kind of alcohol. And okay, so that's here the final product, okay. And for the second another question kind of pretty similar, okay. So that's here the just general kind of 5 membrane, okay. So the second one 5 membrane, okay. So 6 membrane, probably 6 membrane, okay. Right. Okay, and then okay, so we come to question 8, okay. Question 8 probably is the most difficult question, okay. So in the quiz 6, okay. So Dickmann, the condensation, okay. So a lot of students kind of draw kind of wrong step or kind of miss some kind of things, okay. All right, so for Dickmann condensation, okay, so we have the big problem with this one kind of didn't provide too much hint here, okay, and here, okay. So you don't know what's going on, okay. But actually kind of the most important here, okay. So this one goes here, okay. So that means kind of some kind of this one will apply some rule, okay, in the reactions, okay. So most likely like the base, okay. Right. And then for the Dickmann condensation, similar like the other symptom of the Claisen condensation, okay. Normally under the basic conditions, okay. So but now you see kind of here the kind of acid, that's means kind of we start to acid work up, okay. So that's here why we do acid work up, because we generally kind of the more stable kind of intermediate, okay, suck up kind of the second kind of protons, okay. So that's here the little bit kind of most important hint here, okay. All right. So now let's try it, okay. So first one kind of pretty easy, okay. Just pick up the alpha hydrogens, okay. And also kind of delete it, okay. All right, we generally kind of kind of the inolate, okay. So that this is alpha carbon will kind of do the intermolecular reactions with closed ring, okay. So all right, this one, okay. Attack kind of another carbonyl carbon, okay. Open the CO bond, okay. So you have to generate kind of the tetrahedral intermediate, okay. Right. And here, okay, so try it, okay. So probably we can draw the ugly one, okay. So now become kind of the CO single bond, okay. So this oxygen kind of has a negative charge on it, okay. And then there's normal normal charge on this carbon. And then also no lone pair electrons, okay. All right, and then you just let's build a bond between these two guys, okay. So that's 5 membrane, okay. All right, and then afterwards, okay, so when they see the lone pair electron on this oxygen go back, okay, this will kick off the in group, okay. Yeah, that's OR, okay. So that's you get kind of 5 membrane, okay. All right, so now we come kind of here, okay. So this step, okay, so there's no template, okay, that's a little bit harder, okay. So so that you have kind of but a base structure, okay, that's 5 membrane, okay, 5 membrane, okay. So there's the double bond here, alpha carbon, and then another ester, okay. So that's shouldn't be too hard to kind of draw it, okay. It's kind of Oh, SOS, there's one more. Right, so that's the original the alpha carbon K, and then attack the carbonyl carbon K, kick off the link group K, right, and then add a lone pair, so we don't forget to add a lone pair. Right, so why we still need this guy K? Because for the Claisen condensation K, so normally we need to take up the second hydrogens, okay? So that's give kind of more stable kind of the intermediate K. So yeah, so that's the second one coming in K. So yeah, right. So give kind of more stable kind of the carbon cation K, and then we do the kind of the kind of work up K, work up kind of pretty much is still 5 membrane K. And give kind of final neutral compound K. All right. So now this one has kind of negative charge on here, okay? So that's here the work up, okay, to do it, okay? So that's here the here. This one, okay, pick up the proton, okay, and shift here, give kind of water, okay. So that's here the stable product, okay, and then the final step, okay, just kind of give you kind of the final the compound, okay. Okay. Yeah, that's final product, okay. So let's see, okay, so looks like everything's fine. Yeah, so that's here. How do you draw the Dickmann condensation? Okay, so make sure you know how to do it. Okay, because probably in the quiz exam 3 you have kind of similar kind of the questions. Okay, next one is Claisen. Oh, mixed Claisen condensation. Okay, so this one. Okay, so let me see. Okay, right. So a lot of students don't know how to draw the kind of mixed Claisen condensation. Okay, so again you need to find alpha carbon and those here the carbonyl carbon. Okay, and then you can make some kind of letters. Okay, so yeah, that's here help you kind of figure out. Okay, so here's the alpha carbon. Okay, we can get kind of here the alpha 1. Okay, so this is the alpha carbon, alpha 2. Okay, okay, and then yeah, that's carbonyl 1, carbonyl 2. Okay, so C1. C2. Okay, all right. So now we can have all the 4 possible combination. Okay, so the alpha 1. Okay, so can attack kind of the C1. Okay, alpha 1 can also attack kind of C2, and alpha 2 can attack kind of C1. Alpha 2 can attack kind of the C2. All right, so that's here we can draw all these 4 possibility. Okay, all right. So we do it one by one. Okay. Okay, right. So alpha 1 attack C1 as a reactor itself. Okay. Just quickly. Sorry about that. All right. So that's here the alpha attack kind of the C1. Okay. So this is the new bond position. Okay. This one here. Okay. Right. And then second one. Okay. So the alpha attack kind of the C2. Okay. So pretty much each time you just the draw the same thing. Okay. All right. So we have oxygen here, here, and here. Okay. All right, next kind of the alpha 2 attack C1. Okay, so alpha 2 attack C1. Okay. Okay. All right. So that's here the alpha 2, okay. So that's here from here, this guy, okay. Attack kind of here the alpha 1, C1, okay. Right, and then the last one kind of here the alpha 2 attack C2, okay. So this molecule attack itself, okay. Yeah, so that's you get all the full product, okay. And okay, anyway, okay. And so yeah, for the smart work, okay, so yeah, so yeah, they probably only kind of if you get here all four right, okay, you get kind of full credit, okay. So even you draw kind of 1, 2, 3 kind of right, okay, so won't get kind of full credit, okay. When I review it, okay, so yeah, it depends how many kind of the structure you draw, okay, so I can give you kind of partial credits, okay. Don't worry, okay, so yeah, yeah, you can earn some partial credit for this question, okay. Right, and then the last one is yeah, Robinson annulation. Okay, so that's question 10. Okay, some question asked. Okay, did you leave question blank or only one attempt? Okay, yeah, some students kind of leave some question kind of blank. Okay, so yeah. Enough time, it's hard to say. Okay, so yeah, most times students kind of spend like 25 minutes. Okay, so that's average time. Okay, so yeah, some students kind of the much less time. Okay. And so for the yeah, actually kind of some students did pretty well, okay. So I will say one student got kind of 100 kind of the points, okay. So yeah, 100%, okay. So that's quite impressive, okay. Even myself, okay, maybe it kind of got 100%, okay. And then there are kind of 3 students kind of 90% kind of points, okay. So yeah, 90, yeah, 98, 95, 93, okay, something, okay. Something got 80%, okay. So and but we also get a lot of students kind of very poor grade. Okay, so yeah, 20%, 30%. Okay, something like this. Okay, so yeah, it depends. Okay, so yeah, I will say kind of yeah, a lot of kind of practice should make well. Okay, so yeah, the yeah, should be have kind of enough time. Okay, so yeah. All right. Okay. So for Robinson annulation, okay. So yeah, the actually, as long as you know what's going on, okay, shouldn't be too hard. Okay. So yeah, the yeah. All right. So we have these ones alpha. We call kind of the beta diketones. Okay. So that's kind of a real nuclear for alpha carbons. Okay. Right. And then yeah, this is kind of alpha project are situated kind of ketones. Okay. So we'll first do kind of back addition to this carbon, and then yeah, we do intramolecular aldokinesis. Okay. This alpha carbon. Okay. And close ring, okay, with yeah, another carbonyl, okay, on this group, okay, yeah. All right, so for first case, we just kind of draw these 2 molecules, okay. And I tried, okay, so yeah, if you draw some kind of ugly one, okay, it's still working, okay. So let's try it here, okay. No yet, okay. So I only probably gave 1 or 2 question. A student point back. I just start kind of review, okay. Yeah. So the time I will say kind of should be enough. Okay, so the most students didn't even use kind of full 30 minutes. Okay, so only 23, 25. Okay, maybe 21 minutes. Okay, and I have to give some kind of student time back. Okay, all right. So let's focus on this one. Okay, so that's alpha carbon. We'll do micro addition add to kind of this carbon. Okay, so that's first step. Okay, so we can try to draw the ugly one. Okay, all right. So, okay. Let's make sure it kind of yeah. All right, so now yeah, this bond become kind of a single bond now, okay? All right, okay, so that's first step. The second step, okay, so yeah, this alpha carbon, okay, will build up kind of a double bond with the carbonyl carbon here, okay, so that's the aldol condensation, okay, so yeah. So the first alpha carbon add to here, you just kind of aldol, okay, and then following kind of condensation, okay, you just kind of final product, okay, so yeah. Oh, that's long. Yeah, so I will kind of take. So suppose you don't need to know the second step, okay? But I will take a look, okay? So if you draw the first step is right, okay? So I probably give you full credit back, okay? Yeah. So for the smart work, I unfortunately kind of require you kind of draw the both step, okay? All right. So probably so you still only need to know kind of first two step, okay? Don't need to know last step, okay? So yeah. Right, so that's the pretty ugly one. Okay, 1, 2, 3, 4, 5, 6, 6 membrane. Okay, so let's see. Okay, yeah, that's still working. Okay, so for the Clayson Robinson annulation. Okay, so you don't need to know exactly kind of what's the final product. Okay, so as long as you know the don't need to draw the pretty perfect kind. As long as kind of you know what's reaction going on. Okay, should be fine. Okay. All right, so any question about the quiz 6? Okay, for other question, kind of most of them get the kind of right answer. Okay, so and also when I finish go over quiz 6. Okay, so I open it. Okay, so you guys can start kind of still know the answers. Okay, any questions? Yeah, the time. Okay, so really depends. Okay, so most students can will see not exactly kind of miss time, just don't know how to do it. Okay, so All right. Okay. So if there's no further questions, okay, so we'll move to the continue chapter 20, okay, 21, okay. Yeah, if you have a question, you can still type in the chat window, okay. All right, so for the chapter 21, okay, so last time we talked about the stability of radicals, okay, so most stable ones kind of the allylic and also benzoic kind of the radicals, okay, and then followed by kind of the tertiary, secondary, primary, and also methyl, okay. So why is that? Okay, so for the allylic and also the benzoic kind of the radical, okay, so they can have kind of resonance, okay, stability, okay, and then for all other cases, so because of the I will say that's tough, okay. So chapter 20 is kind of pretty tough chapters, okay. So you need to do a lot of practice, okay. So you get perfect, okay. So some students kind of did pretty well, okay. So the some students kind of I don't know why, okay. So so they're just gonna do practice, okay. Work on the homework, okay, and then all kind of the practice, okay. So that should be fine, okay. So if you get kind of poor in the chapter 20 quiz 6, okay, that's be fine, okay. So most students kind of didn't get the idea great, okay. So but unfortunately, okay, so that's why I told you kind of in the first class, okay, chapter 20 is hard one, okay. You don't expect kind of easy life for the chapter 20, okay. Yeah. So only complaint kind of from is actually I will say the Dickmann condensation kind of mechanism. Okay, other reaction I won't say kind of take too much time. Okay, so other the questions. Okay, yeah. All right. All right. Okay, so let's do a little bit of focus on kind of chapter 21. Okay. So here, okay, so first thing kind of wide stability of we call kind of allylic and benzoic kind of the radicals, okay. Right. So reason for that kind of they have kind of resonance structures, okay. So for the I just give you guys kind of one example, okay. Right. So for allylic the radicals, okay. So actually kind of that's the first time we draw kind of radical resonance structures, okay. So let's kind of go like this way. shared electrons, okay, pi electrons can go like this, okay. Okay. So yeah, this new pi bond actually kind of assembled from the one original kind of radical electrons and also one electron from this pi bond, okay, and then you get kind of another pi bond electron as kind of radical electrons, okay. So yeah, the same thing you can actually draw the kind of the radical kind of the resonance structure for the benzoic radical, okay. So yeah, that's actually has more kind of the resonance structures, okay. So because you can delocalize kind of the electrons into kind of whole pi bond system, okay. That's why the kind of the Ali kind of benzoic radical kind of more stable, okay. And for the other radicals, okay, pretty much you can treat it as kind of carbon cation, okay. So carbon cation, okay, so tertiary more stable than secondary and followed by kind of primary and followed by kind of the methyl, okay. So yeah, you can actually kind of treat the radical as kind of the electron deficiency space, okay? Electron deficiency space, okay. Yeah, because normally for the atom or kind of a molecule, they have kind of follow kind of octet rule, okay, so has 80 electrons, okay, but now you miss one electrons, okay, become kind of some kind of the orbital has only one electron. Electron deficiency case, so that's pretty much similar like the cation case. So if you have kind of more RQ group case, so they can have kind of the hyperconjugation, okay, donate electron into the center radical carbons, okay, something like this. Yeah. So make that's the center carbon not so kind of electron deficient, okay, and then kind of stabilize, okay. So the more R group, okay, you have kind of the higher stabilities, okay, and so yeah, for the hydrogen case, so there's no such kind of hyperconjugation effect, okay, so that's why kind of the methyl and also the primary kind of last stable, okay, so yeah, right, so please keep this one in mind, okay, so because that's determine kind of reactivity of kind of some later reactions, okay. Right, and then the radical, the carbon radical kind of geometry, okay, so there are kind of the two theory about kind of radical kind of real the molecular shapes, okay. One just said kind of the center carbon, okay, so radical carbon actually kind of the sp2 hybrids, okay. This single electron in kind of the p orbitals, okay, and the whole molecule kind of like the trigonal planar structures, okay. But another theory kind of this carbon actually kind of sp3 hybridized, okay, so that's the the tetrahedron kind of the electron density kind of the geometry, okay. But because this the orbital kind of too small, okay, so this the three kind of the RQ group can quickly shift up and down, okay, so average it out, okay, so these two configuration, okay, so this the just repeated kind of invert kind of pyramidal kind of radicals, okay, and average out, okay, so eventually it looks like these three R group, okay, actually kind of on the same plane, okay. And for you guys, just treat these three R group on the same plane, okay, for the radical reactions, okay. So that's why kind of the radical reaction normally has no stereochemistry, because that's different from chapter 2, okay, chapter 22, okay. Chapter 22, okay, we said kind of a lot of stereochemistry, okay, but chapter 21 no stereochemistry, okay. So because the radical geometry is kind of planar, okay. All right, okay. So for generation of the radical, okay. So generation radical actually kind of a couple of ways, okay. The first one kind of the thermal ways, okay. So you just heat up kind of the solution, okay. But you need to add kind of some we call the radical initiators, okay. So if you only heat up, okay, so normally you won't have kind of the reaction happen, okay. But once you add kind of initiator, okay, that can have kind of reaction happen, okay. So two kinds of initiator, okay. So one is kind of peroxide, okay. Okay, peroxide is kind of this kind of structure, okay. Yeah. So there are kind of the two oxygen in the middle and two R group, okay. And so because this the bond between the two oxygen normally quite weak, okay, because the oxygen kind of strong electron withdrawing can break up this bond easily, okay. So under the heat, okay, so that's evenly break up these two kind of bond, okay, two kind of electrons, okay. So we call kind of homolytic kind of kind of cleavage, okay. So that's the openness and then you generate kind of the two radical, okay. And this one kind of the initiate can react with kind of another molecule and kind of push the electron forward, okay. And but nowadays case, so the more common kind of the radical initiator called kind of the ozone compound, okay. So ozone compound normally have this kind of structure, okay. So而且the two nitrogen and then two alkyl group, okay. So on each nitrogen, okay, the theta bond, okay. And so for this, the ozone compound, okay. So once you heat up, okay, so the nitrogen will be gone, okay. And then once nitrogen gone, you generate kind of two alkyl kind of the radicals, okay. So plus. Right. So this one actually kind of more efficient, okay. So and one of the most famous kind of the radical is kind of the initiator called kind of AIBN, okay. So that's shown here, okay. And the full name kind of azobc, isobutyl, butyryl kind of nitrite, okay. So for you guys, don't need to remember its structure and also their full name, okay. So only need to remember kind of AIBN, okay. It's a kind of radical initiator, okay. That's all, okay. So it kind of cause the radical reactions, okay. Similar like we learned before, kind of dipole, okay. So you don't need what dipole looks like, but just remember kind of dipole is kind of reducing reagent, okay. So okay. All right, AIBNK. Right, so that's the one way, okay. So thermal condition with kind of a radical initiator, okay. The second way is kind of the photo conditions, okay. For photo condition, kind of normally you strike the reaction solution with kind of UV light. Sometimes nowadays can even use some kind of variable light kind of you can initiate kind of radical reactions, okay. And so so for the photo reaction we learned in the previous chapter, okay. So you just kind of the arrow put kind of H mu, okay. So that's means kind of photo reaction, okay. So the people know what's that kind of reaction, okay. And then don't need use other reagent, okay. So all right, okay. So that's the radical reactions, okay. So why we will study kind of radical reactions, okay. So the one case is kind of so far we haven't learned any reaction about kind of arcane, okay. Arcane, okay. All right. So you can try to look at your kind of previous notes, kind of previous letter, okay, a previous kind of a chapter kind of slides, okay. You'll find kind of we learn a lot of reaction kind of archaic or some kind of alkyl halide carbonyl compound, okay. So but non-reaction for this one, okay, right. And but the arcane is kind of actually kind of pretty important kind of chemicals, okay. So I guess probably the petroleum kind of industrial kind of produce kind of the arcane compound, okay, like the gasoline case. So probably like the kind of billions of tons each year, okay. So that's probably one of the most abundant chemical kind of from kind of nature, okay. So we have to take fully advantage use of the arcane, okay. So we can convert kind of to some kind of the better chemicals, okay, for some other reaction, just not kind of just burn it for the kind of as gas, okay. So actually kind of radical reaction can convert arcane to some other chemicals, okay. So that's why it's kind of radical reaction kind of important, okay. Right, and then reaction we learned here called kind of the radical halogenation, okay. So this one, okay, convert arcane to kind of the haloarcane, okay, also called kind of the kind of the alkyl kind of halide, okay. Right. So that's the radical kind of halogenation, okay. Okay, so for the overall reaction, actually kind of you have kind of the R. Okay, so that's the H. Okay, so I just kind of list. Okay, and then react with kind of halogen. Okay, so most common halogen kind of the chloride or bromide. Okay. Okay, and then you can use kind of the UV, okay, as kind of the initiate kind of a radical reaction. You can also use kind of a heat with kind of radical initiator. Okay, so also fine. Okay, once reaction done, okay, pretty much you just like here this kind of the substitution reaction. Okay, one hydrogen from alkene replaced by kind of halogens. Okay, so yeah, Br or Cr. Okay, and then H will pick up kind of another hydrogens. Okay, so yeah. Okay, so that's the overall reaction. Okay. Okay, and so the case thing about the reaction mechanism. Okay, so that's okay. So maybe so the little bit somehow different from kind of the reaction mechanism kind of we learned before. Okay. So this what's going on here? Okay. So that's actually kind of the take here the three-step finish reaction. Okay, so that's the actually kind of the different from kind of reaction we learned before. Okay, so I'm going to draw the kind of the mechanism. Okay, so you guys gonna just follow me. Okay, because that's kind of required mechanism for the chapter 21. Okay, right. So for this reaction. Okay, so normally we take three steps. Okay, the first step kind of initiation. Okay. Initiation, okay, so what happened kind of the chloride, okay, so the molecule, okay, break up into radical first, okay, so all right, go like this way, okay, so it's arrow, okay, so make sure you kind of the which called kind of fish-hook arrow, okay. All right, you generate kind of chloride, kind of kind of radicals, okay. Right, and then next kind of we move to kind of propagation, okay. So that's we have kind of initiate kind of the radicals, okay. Right. Propagation, okay. So this chloride radical will react with kind of alkene, okay. So here we just use kind of this methane as example, okay. So build up bond between kind of chloride and also H, okay. So the chloride contribute one the protons, okay, and then the hydrogen, okay, contribute another kind of the electrons, okay, and then you give this electron another electron give to kind of the carbon, okay. So that's you see kind of what's going on, okay. Right, and then once reaction is done, okay, you generate kind of the HCl, okay. Plus kind of methyl radical, okay. This should be kind of C. Carbon, okay. Right. Okay. So once this step's done, okay, so this methyl radical will react with another chlorine molecule, okay, and then give kind of the methyl chloride, okay. Right. So what happened kind of now this methyl the single electrons, okay, build bond with kind of this chloride kind of the shared electrons, okay. So now kind of one build up kind of carbon chloride bond, another kind of gives to the second kind of chloride, okay. Then you generate kind of the chloromethane, okay, plus the chloride radical, okay. Right. So the two propagation step, okay. So right. So once you generate kind of chloride radicals, okay. So this one can be recycled, okay. Go back here, okay, and react with kind of second kind of methane kind of molecule, and then you continue this circle one and one more and more. You can eventually kind of consume all kind of methane molecule and also all kind of chlorine kind of molecule, and then generate kind of final product kind of the methyl chloride, okay, and also HCl, okay. Okay, and then yeah, once yeah, the most of the yeah, muffin and also chloride molecule are consumed, okay, and then we move kind of leave a little bit of space here, okay, leave a little bit of space here, okay, and then we move kind of yeah, termination kind of yeah, stage, okay. Right. So for termination, okay, so yeah, yeah, just yeah, the quench all the kind of radicals, okay. So there are kind of three possible kind of yeah, yeah, termination reactions, okay. One's kind of yeah, the two yeah, chloride kind of radical meet each other, okay, and then you build a bond kind of yeah. Right, so two chloride, okay, so like this way, so okay, each contribute one electron, okay. You generate kind of yeah, chloride molecule, okay. Right, another one kind of chloride yeah, radical meet with kind of yeah, methyl radicals, okay. Yeah, let's show like this, okay. Over here, okay. So this one also can give you kind of the yeah, methyl yeah, the yeah, chloride, okay. The last one just kind of yeah, two methyl radicals, okay. So yeah, we draw like probably this way. Meet each other, okay, and then we generate kind of ethene, okay. So yeah, each contribute kind of one electrons, okay. Yeah. So in the termination step, okay, so it's kind of yeah, all radical is gone, okay. Yeah. All right. And for the reality, okay, so yeah, yeah, make sure yeah, you know how to draw this kind of yeah, radical kind of yeah, reaction, okay, radical hydrogenation, okay. So for reality, actually kind of yeah, you only need one initiation step, okay. So yeah, as long as you generate kind of yeah, the somehow like yeah, radical initiator, okay. And then yeah, there's many kind of yeah, propagation step, okay, circles, okay. So yeah, continue kind of each step you generate kind of new radical and consume some kind of starting material, okay, and then yeah, you generate kind of new radical and again, okay. So 1,000 times, okay. And eventually, once you consume kind of all kind of the molecules, okay, and then only radical left, okay. So radical kind of left, okay. So yeah, kind of yeah, one step, okay, one termination step, okay. So to the kill all the radicals, okay, finish the reaction, okay. And so that means kind of yeah, for the real reactions, okay. So yeah, just yeah, very yeah, the small numbers of yeah, the initiation and also yeah, termination, okay. Main reaction are kind of yeah, the propagation, okay. Propagation kind of yeah, you do many times, okay. And then yeah, for the overall reaction, okay, actually kind of yeah, you just add yeah, these two main reactions together, okay. Right. So once you add together, okay, so you cancel out kind of yeah, the radicals, okay. So yeah, here, here, and then that's your kind of yeah, overall reactions, okay. So yeah, on the left molecule you have kind of yeah, the methane plus chlorine, okay, and then on the right molecule you have kind of yeah, the methyl chloride, okay, plus kind of HCl. Okay, so that's the overall reaction, okay. So for the radical reactions, okay, so yeah, yeah, that's mechanism for different from kind of yeah, yeah, previous yeah, mechanism we learned, okay. So yeah, so yeah, you have to know how to draw kind of yeah, all three steps, okay, so initiation and then propagation and then termination, okay. And then yeah, understand kind of yeah, propagation actually kind of yeah, main reaction, okay. So that's you give kind of real yeah, the final yeah, the reaction product, okay. So that's yeah, something can be bad, okay. So probably next yeah, yeah, Thursday kind of class we'll do a little bit more practice, okay. So that's yeah, yeah. I promise you, okay, so yeah, you'll see kind of a radical reaction mechanism, okay, so in the final exam, okay, not exam 3, exam 3 probably, yeah, want to cover kind of the, yeah, chapter 21, okay. Yeah, exam 3 only cover the chapter, yeah, 19, 20, and also 22, okay. All right. Okay, so yeah, that's here the yeah, mechanism, okay. So now we need to compare kind of here the radical chlorination and with bromination. Okay, one kind of here the yeah, then kind of here the chloro kind of here the arcane, another kind of bromo arcane, okay. So for the yeah, chlorination, okay, so yeah, big problem kind of yeah, multiple chlorination, okay, and also no serial selectivity, okay. So we'll do it one by one, okay. So what means multiple chlorination, okay? So yeah, if you yeah, even yeah. Try to kind of put a reagent amount in 1-to-1 ratio, okay. So for example, yeah, one kind of molar of the methane, one molar kind of chloride, okay. So yeah, you try to do this reaction, okay. So yeah, but eventually you should get kind of yeah, all the possible kind of the mixtures, okay. So yeah, kind of the monosubstitute kind of here the methane, disubstitute methane, trisubstitute methane, and even kind of here tetrasubstitute methane. Okay, and then it's kind of we call kind of here the hard to kind of stop at kind of monochlorination, and then you got kind of here the polychlorination mixtures. Okay, so that's here that makes things kind of tough. Okay, because they're kind of mixture and they don't know which kind of major product. Okay. And so another problem kind of if you have kind of more than one kinds of the protons, okay, so you have kind of unsymmetrical structures, okay, so then there's kind of less selectivity for the chlorination, okay, so you can have all the possible kind of the proton be replaced by the Cl, okay. So for example, okay, so this here is the isobutene, okay, isobutene, okay, so has two kinds of protons, okay. Totally 9 kind of methyl proton, and then middle there's kind of the tertiary kind of protons, okay, all right. So when you have the reaction happen, okay, so the both proton can be replaced by kind of Cl, okay. So in this case, if you want to do kind of isobutene kind of radical chlorination, okay, so actually kind of a lot of product, okay. So you can kind of the terminal hydrogen replaced by Cl, internal hydrogen replaced by Cl, also kind of polychlorination, okay. So that's pretty difficult kind of isolate any of this one, okay. So last kind of valuable kind of make kind of pure compound, okay. All right. So the reason for that kind of for the radical chlorination, okay, so this one reaction kind of generate a lot of heat, okay, so we draw, okay, so we draw the energy diagram, okay, something like, okay, isothermal reactions, okay, so and then this heat kind of push reaction happen quickly, and then you just cannot stop it, okay, so and then also last choice, okay, so pretty much kind of we call kind of the kinetic control, the kinetic control kind of whenever kind of have the reaction happen, that's just happen, okay. So for you guys, okay, so just keep in mind, okay, so for the chlorination, okay, so last selectivity, okay, so you can get polychlorination product, also kind of no kind of selectivity for kind of certain protons, okay. But when we come to kind of bromine, okay, stratical bromination, okay, that's much better, okay. And so we can get kind of the more selective kind of the positions, and also kind of generate only mono bromine kind of bromo kind of compound, okay. A reason for that kind of for the bromination, okay, so the reaction actually kind of especially first step, okay, so we call kind of rate limiting step, okay, so that's the energy diagram like this, okay. All right, so that means kind of first step kind of much more slow, okay, so you need to give kind of enough energy, okay. So if it's the reaction take time, okay, so then you can generate kind of more stable kind of the tertiary radical, okay. So that's if you have kind of the different kind of protons, okay, in one molecule, okay. So I will give you kind of one example, okay. Oh, it's here, okay. So if you have kind of different protons, okay, in one molecule, okay, and then the proton can give kind of more stable radicals, okay, and that's you get kind of the ideal kind of the bromine kind of bromination kind of compound, okay. All right. For example, okay, so this kind of we still kind of the isobutyl, okay, so So isobutyl, okay, so if you cleave for kind of terminal hydrogens, okay, for example, this one, okay. If this one is gone, okay, so you generate kind of primary kind of radicals, okay. And then if you use another color, okay, remove kind of the center kind of hydrogens, okay, that's you generate kind of the tertiary kind of radical, okay. So we just learned the very beginning of this class, okay. Tertiary radicals are much more stable than kind of the primary, okay. So that's for bromination, okay, so you can distinguish these two kind of radicals, okay, and then eventually, okay, so the bromide, okay, will go to kind of this internal kind of center carbons, okay. So that's why the selectivity high kind of here, okay, so and also showed you some kind of example here, okay, so here we have kind of some kind of toluene kind of nitrotoluene, okay, so and then if you cleave off these protons, okay, you generate kind of we call the benzoic radical, benzoic radical pretty stable, okay, so that's easy kind of proton BR, okay. Okay, so this one we do it probably next class, okay, so All right, so yeah, that's it for today's class, okay? And so we'll continue this chapter on Monday, okay? So yeah, probably on Monday we can finish chapter 21, okay? So yeah, on Wednesday, okay, so yeah, we'll do some kind of polymer chemistry, okay? So yeah, and then on Friday, okay, so next Friday, okay, so we'll do a little bit summary about kind of chapter, the whole organic chemistry too, okay? Help you guys kind of prepare kind of final exam, okay? And then that's all, okay? So yeah, no more class, okay? Yeah. All right, any questions? Yeah, thank you, okay? Appreciate it, okay? Officer, okay, so yeah, if you have questions, okay, so yeah, you can still keep your Zoom open, okay? Keep your Zoom open, okay? And I'm glad to answer you any question, okay? Any kind of the homework, okay? Or kind of the lab kind of report questions, okay? So yeah. Yeah, we will have kind of the exam 3, okay? So exam 3 will be on Tuesday, okay? That's we voted kind of the probably on Wednesday, okay? So yeah, exam 3 on Tuesday cover chapter 2019 and also 22, okay? This final going to okay, so one by one, okay. Final, okay, final pretty much similar like the exam, okay, but it's double amount of questions, okay. So yeah, because the final exam take like 2 hours, okay. So yeah, the expect kind of the more question, okay. One difference is kind of some kind of all the homework, exam, and quiz question, okay. I will put in kind of final exam, okay. So you will see some kind of the previous kind of questions, okay. So in the homework, okay. So that's make sure you know the how to kind of give the answer for those questions, okay. Yeah. And when's post lab due, okay. So yeah. Post lab, okay, so if you completed the lab 7 this week, okay, so yeah, that's due in the checkout week, okay, so yeah, next week, okay, so yeah, when you do the checkout, okay. But yeah, if you want kind of quarantine or kind of some kind of makeup or whatever, okay, so yeah, once you done the makeup, okay, so yeah, the post lab due 1 week later, okay, so that's the plan, okay.
Oh yeah.
Okay, all right. So any question? Okay, so no more question. Okay, so
Yeah, I just had a question on the